For decades, the standard model of particle physics has been considered one of the greatest achievements in science. It predicts the behavior of fundamental particles with extraordinary precision. Electrons, quarks, neutrinos, photons. Their properties are calculated to astonishing accuracy. Experiments confirm these predictions again and again, but the standard model is not complete. It does not include gravity. It does not explain dark matter. It does not fully explain neutrino mass. And recently, experiments have begun revealing tensions that are difficult to ignore. One of the most intriguing involves the muon. The muon is similar to the electron, but heavier. It behaves like a spinning, charged particle interacting with quantum fields. According to the standard model, its magnetic moment, the way it wobbles in a magnetic field, can be predicted with extreme precision. In theory, the value is fixed, but measurements at Fermilab's Muon G to experiment suggested something different. The muon's behavior appeared slightly off. The difference is tiny, but in precision physics, tiny deviations matter. They may signal the influence of unknown particles, unknown forces, or physics beyond the standard model. For years, the anomaly hovered at a significance level just below the threshold required to claim discovery. New data, refined measurements. The tension remains under intense scrutiny. This is how revolutions begin in physics. Not with explosions, with discrepancies. If the muon is influenced by particles we have not yet detected, then something fundamental is missing from our current framework. And it is not alone. At CERN, anomalies in BME-SON decays have suggested potential violations of lepton universality, the principle that electrons, muons, and tau particles should behave identically under certain interactions. Some measurements hinted that muons behave differently than electrons in rare particle decays. If confirmed, this would be extraordinary. It would mean one of the foundational symmetries of the standard model is incomplete, but science moves carefully. Additional data has reduced some of these anomalies. Others remain inconclusive. The situation is not settled, and that uncertainty is powerful. Physics advances when predictions and measurements diverge. But divergence must be verified repeatedly. This tension between theory and experiment is where discovery lives. The standard model has survived decades of testing. The Higgs boson, discovered in 2012, confirmed the final missing piece of its particle catalog. Yet, even with the Higgs confirmed, the model cannot explain why the universe is dominated by matter rather than antimatter. It cannot explain why neutrinos have mass. It cannot explain the invisible mass shaping galaxies. It works beautifully, but not universally. This is what makes the current moment so interesting. The cracks are small, but they are consistent. Particle accelerators push energies higher. Detectors become more precise. Theoretical calculations improved. And still, questions remain. If new particles exist beyond the standard model, they may be heavier than we can currently detect. They may interact weakly. They may hide in subtle deviations rather than dramatic signatures. Some physicists propose supersymmetry, a symmetry linking known particles to heavier partners. Others explore composite Higgs models, extra dimensions, or new gauge bosons. So far, no clear breakthrough has emerged. But absence is not emptiness. The lack of detection narrows the field. It constrains possibilities. It tells us where new physics is not. This is how science refines itself. Meanwhile, neutrinos, nearly massless particles that barely interact with matter, continue to surprise researchers. They oscillate between flavors as they travel, implying mass. But their mass is incredibly small and still not precisely determined. Why do neutrinos have mass at all? The standard model originally predicted they should not. Something modified the picture. And then there is dark matter. Galactic rotation curves and gravitational lensing show that visible matter accounts for only a fraction of cosmic mass. Something unseen dominates. But after decades of searching in underground detectors, space observatories, and particle colliders, no dark matter particle has been conclusively identified. This is unusual. When something affects gravity at cosmic scales, physics expects it to show up elsewhere, yet it remains hidden. If dark matter interacts only gravitationally, that would challenge expectations. If it interacts weakly, we should eventually detect it. The universe is not aligning neatly with our theories. And that tension is the heartbeat of modern physics. We are not witnessing failure. We are witnessing pressure. When pressure builds between prediction and measurement, frameworks either expand or collapse. The 19th century believed Newtonian mechanics was complete. Minor anomalies led to relativity and quantum mechanics revolutions that redefined reality. Today's anomalies are subtler, but subtlety does not mean insignificance. The muon may yet align perfectly with theory after further refinements, or it may remain a signal of hidden structure. BM-son decay anomalies may disappear with better data, or they may point to new forces. Science is in the middle of the process, and that is rare. We are living in a period where the next fundamental shift could emerge quietly from statistical deviation. The universe is not contradicting physics. It is challenging. It is challenging. And that challenge is the most exciting thing happening in science today. Still, within